But absolute is typically the terminology used over global, but they mean the same thing. So the absolute maximum, it would be at C as long as f of C is greater than or equal to f of x for all x in D, where D is the domain of f. And then that number, f of C, whatever that y value is called the maximum value. So it is the absolute highest value of a function if there is one. Some functions don't have an absolute maximum. And then an absolute minimum, similarly, would happen at C if f of C is less than or equal to f of x for all x in D. The number f of C is called the minimum value, so it'd be the absolute lowest value of a function, again, if there is one. Some functions don't have an absolute min. And then these are called the extreme values of a function. So on this diagram that you have here, this particular function does have, so these ends here would be endpoints. It's not continuing. So there would be an absolute max and an absolute min for this graph. So this absolute maximum would occur at the x value D. Yeah, so f of D would be, I'm going to just abbreviate the absolute max. And then what would the absolute minimum be? A. A is a little lower. So f of A is the absolute minimum. Okay, and we're going to be looking at the same graph then for the relative extrema. So here we've talked about, and we've already referred to local maxes and mins. So local max or relative max mean the same thing, local min, relative min. So this is if you limit a specific interval. So if you're only looking, say, near a value C, if that's the highest value on a certain interval, it's called a local max or a relative max, and then a similar definition for a local min, relative min, but we've worked with these already. So informally, we know these are the hills or the valleys on a graph. And what I do want to point out is that an absolute max or min can also be a local max or min, but it doesn't have to be. So, for example, on this graph again, I'll say this. There are two local maxes and there are two local minimums. So here at B, where that hill is, f of B would be a local max. And then the other local max is the absolute max. So f of D is not only the absolute maximum, but it is also a local maximum. And then there are, like I said, there are two local minimums. So those can occur at a valley, like at E. So f of E would be a local min. But at C, that is also considered a local minimum, because if you restrict your interval at C, that would be the lowest point, even though it's not an actual valley. So I'm just going to do this here. So f of C and f of E would be local minimums. So then f of A is the absolute minimum, but it's not a local minimum, because, if you want to make this note here, a local max or min cannot occur at an endpoint. And that's because if it's at an endpoint, you really need that interval on either side of an x value or a y value to say, okay, on this interval, that's the lowest or highest point. And so you don't have that interval on both sides of an endpoint. You just have the graph on one side of it. So an endpoint cannot be a local max or min, but it can be an absolute max or min. That's just kind of tying some terminology that you're already familiar with. And the idea in this section is how are we going to use calculus to find these parts of a function. So keep in mind, again, Yes, if you have a graphing calculator, you can always graph a function, but you are not allowed a graphing calculator for everything. So you need to be able to find absolute or local maxes and mins without graphing a function. So for example 1, I just have a few different functions, and it says use the graph of each function to state the absolute and local max and min values of the function, and I'll show you how I want you to state those values as well. So for A, and if you needed to for these, you could always pull these up on a graphing calculator because it does say to use the graph. But for f of x equals cosine of x, I'm just going to sketch one period of that graph. But again, if you needed to on a graphing calculator, you could graph it. So I know cosine starts at the y value 1, that goes through at pi over 2, is negative 1 at pi, goes through 0 at 3 pi over 2, and is back at 1 at 2 pi. And then it would continue on either end. So I'm just drawing the one period of it. Okay, so then the question is, does the graph of cosine of x have an absolute maximum value? Does it have an absolute maximum value? So it has, well, it has one absolute max, but it occurs at multiple places, right? So what is the absolute maximum value? 1. So it's the y value. It just occurs infinitely many times. So I can say well, if you made it an endpoint, it still would be absolute. If it's an endpoint, it wouldn't be a local. Yes. Yeah, if it was strictly from 0 to 2 pi, there wouldn't be a local max. So there's an absolute, I'm going to say absolute, because all of these absolute maximum values, I mean, it's the same y value, they're also local maxes. So there's an absolute and local max at, and I know it's at the y value 1, but how I'd like you to write it is I'd like you to use function notation to say it occurs at f of what x value or values, and then what it equals. So where it occurs and then what the value actually is. Dylan, did you have a question? You're referring to like what's happening at C here? So yes, this means, so you know the derivative wouldn't exist there. We're going to be getting to that point. So when you're actually looking for local maxes and mins, you have to consider the derivative might not exist. Yes. You're thinking ahead. So how would I write where these local maximums and absolute maximums occur? It would be. Okay, and then there's also similar idea for the minimums, absolute and local minimums. So there's an absolute, all of the absolute minimums are also local. I want to write where those occur. And that y value is -1. So where do all of the minimums occur? Or how would you write that? It's not pi n. Pi, yeah, so it does occur at pi and then every 2 pi. So you'd have to write it like pi plus 2 pi n. Okay, so recognizing that all of those max and mins are both absolute and local. Unless you restricted a specific interval, then there may not be a local max or min, depending on the interval. So then for b, we have f of x equals x squared. sketch what this looks like. So it's a parabola. Vertex is at 0, 0. What? Vertex is at 0, 0. Is there an absolute maximum for x squared? No. Is there a local maximum? No. So there's no absolute or local max. How about minimum? Is there an absolute minimum? Yes. At 0, 0, it's also a local. So I can say absolute and local min at f of 0 equals 0. All right, and then for C, x cubed. So x cubed, just the function x cubed, does not have that local max or min in the middle of it. So there isn't a local max or min. Is there an absolute max? No. Absolute min? No. So there are no, you could say this then, no absolute or local extrema. Fancy vocab there. Okay, and then I think we get the idea for D. I'm going to come back to D if there's time here. There is a way, and some of you I know already know how to do this. There's a way if you graph a function on your calculator to have your calculator approximate or find where max and mins occur. But I want to make sure, this I can always show you in other examples. I just want to make sure we do get through the critical values at least at the end. So we can come back to D, even if it's a different day, we can come back. So for the next part, this is actually where the extreme value theorem comes up. So as you can see, some functions have extreme values, others do not. So if you are trying to determine if a function has extreme values, there's a theorem that gives conditions under which a function is guaranteed to possess extreme values. So again, like the intermediate value theorem, you're not actually using the theorem to find the values themselves. It's just saying whether or not they exist. So how to know if a function is guaranteed to have extreme values? The extreme value theorem states, if f is continuous on a closed interval from a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers, c and d, in the interval from a to b. So pay attention to the conditions of that theorem. In order for it to possess an absolute max and an absolute min, f has to be continuous on a closed interval from a to b. So for any function, if that is true, then there is an absolute max and an absolute min. It doesn't tell you what it is, but you know that it would exist. So there's 3 graphs below that I just want to point out a couple of things. And then all of these graphs to these are end points. They're not meant to be open circles here. They are filled in. Okay, so in the first one, In the first one, where do the absolute max and min occur? At C and D, and how else could you describe C and D? Local maxes and mins. So absolute extrema can occur at local extrema. So we're kind of working towards how would we be able to find absolute maxes and mins without actually looking at a graph. So here this is saying if we could find the local maxes and mins, then those could possibly be the absolute maxes and mins. So then for the second graph, the local or the absolute max still occurs at the local max. Notice though that the absolute min occurs at the end point. So absolute extrema can occur at local extrema. Absolute extrema can also occur at endpoints. Because by the extreme value theorem, the function has to be continuous on the closed interval, so the endpoints have to exist. And then the third graph is just showing, and we saw this with our trig function cosine of x, that absolute maxes and mins can occur at more than one x value. That's what that is showing, and we've covered that idea already. So what I included example 2 for was just for you to look at those two graphs and say, or I want you to state what the absolute max and min values are, and if they don't have either an absolute max or min, ask yourself, well, is that contradicting the extreme value theorem, why or why not? And on these graphs, it's not very clear. This is a closed dot, as is at 2, as is here. And then otherwise this circle in the first graph, the very top one, is open. And for graph B at 1, that is also an open circle. So if we look at A, we can look at these together quickly here before we move forward. At A, does this graph have, and we're just looking for absolute, not local, does it have an absolute max? Okay, if you're saying yes, what is it? For the first graph, there is an f of 1, but f of 1 is here. Technically. Because I filled mine in. Okay, so for A, this, because it is open, it is not filled in, that point doesn't exist. 3 is not the absolute max. It never reaches 3. But you still can't say there's an absolute max because it is getting super, super close to 3. So there is no absolute max. Is there an absolute min? Yes. There would be an absolute min at, and that would occur at 2, 0. So f of 2 equals 0. So then, because there's not an absolute max, the extreme value theorem states that there will be as long as the conditions are met. What condition is not met for this function? It's not continuous. So we can say here, it's not continuous on the closed interval from 0 to 2. So therefore, it doesn't contradict the extreme value theorem with the fact that it doesn't have an absolute max. So then for B, does B have an absolute max? No, this is continuing up. There's no endpoint there. So there's no absolute max. Is there an absolute min? No. Because it's open, yes. So it never actually reaches that point. So no absolute extrema. Does that contradict the extreme value theorem? What? Not a closed interval. So the extreme value theorem says it has to be continuous. This function is continuous, but it's not on a closed interval. This is continuous on the open interval. So it's not, I'll just put it's not a closed interval from 0 to 2. It's an open interval. Yes. So you'd have to have endpoints at the two ends. So the fact that there's an asymptote and the fact that this endpoint is technically open means it's not closed. So those are the two things you have to pay attention to for extreme value theorem. Continuous function, closed interval. So then this is now, like I said, this is all leading into how do we find these on our own. So the extreme value theorem says a continuous function on a closed interval has a max value and a min value, but it doesn't tell us how to find them. So we can start looking for the extreme values at the local extreme values, because we said above an extreme value could occur at a local max or min, but it could also occur at an endpoint. Those are the two places we're going to look. Think of how would you use calculus to figure out where a local max and min would be. If I did not give you a graph, how would you determine where a local max or min could be? Okay, find where the derivative is 0, or, Dylan, what did you say before? Find out where it doesn't exist. Because, yeah, if you look back at the front, this here, that peak is a local min. The derivative would not exist there. But it is a local min, and therefore could be an absolute min on a function. So to find local extreme values, you can look to see where does f prime of x equal 0, or where does f prime of x not exist, or where is it undefined, would be another way to phrase that. Okay, and that's just a note. We're going to be still continuing on with this. Okay, so I do want to make sure we get to example 4. Before we get there, though, there's a theorem called Fermat's theorem. And it says if f has a local max or min at c, at some x value c, and f prime of c exists, then f prime of c is 0. Okay, now, I have on here is the converse of that theorem true. We've already talked about this idea already. Converse would be where, yes, it's, well, the negative, I guess, of both. So, well, this is the converse I've written here. F prime of c is 0. Can we say then that it has a local max or min? So if the derivative is 0, is it guaranteed to be a local max or min? Because this says if it is a max or min, the derivative is 0. But can we say the reverse of that, the converse? So the answer to that is no. And I have an example here. I'm just going to show you the graph to make sense of this. X cubed, and this is maybe a poor drawing, but here at this value, the tangent is horizontal. So f prime of x at that point would be 0, but it's not a local max or min. So remember that when the derivative is 0, it could be a local max or min, or it could just be the flat part of a curve. So Fermat's theorem says if you know it's a local max or min, then the derivative is 0 as long as it exists. But if you just know the derivative is 0, it's not guaranteed to be a local max or min. You'd have to look further to see, is it actually a local max or min, or is it just a flat part of a curve? And we'll be looking at how to figure that out. And then this is the other case, if f prime of c doesn't exist. And I just had this example for the square root function, or not the square root, the absolute value function. So the idea we talked about already here, this would be the absolute and local max of that function. However, we know the derivative wouldn't exist there. So this is all leading to what a critical number is. And what we already talked about, Fermat's theorem suggests we should start looking for extreme values of f at the number c, where f prime of c is 0, where it doesn't exist. That's just a little more detail into why. And that gets us into what a critical number is and finding critical numbers. Okay, so here a critical number is defined to be a number c, and c is an x value. So it's a number c in the domain of f such that either f prime of c equals 0 or f prime of c doesn't exist. So keep in mind we are continuing with 4.2 tomorrow. I'm ending with just finding critical numbers. So when you are looking for absolute maxes and mins of a function, you start by looking at the critical numbers. You start by looking to see where is the derivative 0, where does the derivative not exist. So if you are just asked to find the critical numbers, you are just finding, in this case we have a function capital F of x, we need to find where does capital F of x equal 0, where does capital F of x not exist, or where is it undefined. Okay, so we need to find the derivative first. How do you find the derivative of this function? Yes, product rule. Let's see. All right, so the first would be x to the 4/5. Second is the quantity x minus 4 squared. So what's the derivative of x to the 4/5? Negative 1/5, yep. And then derivative of x minus 4 quantity squared. Yes, and then don't forget it is the chain rule. Now this is just times 1. The derivative of x minus 4 is just 1. But don't forget that if it, say, was 3x minus 4, that you'd have the times 3 there. So it is just 2 times the quantity x minus 4. So derivative f prime of x with the product rule first times second prime. So it would be, I'll write it as 2x to the 4/5 times the quantity x minus 4 plus second times first prime 4/5 x to the negative 1/5 times the quantity x minus 4 squared. Okay, so you find the derivative, then you find where does that equal 0, where does it not exist. Now, we have a couple minutes here. I picked a more complicated function, but I know we're going to run out of time. What I would do in this case is, here's a case where you need to simplify this in order to figure out where does it equal 0, where does it not exist. So it's not just, I'm going to solve this with my calculator, because what if you're not allowed to use one? So what I would do to try and simplify this, and we can pick up with this tomorrow, you should still be able to, as long as you understand what it means to find a critical number, you could still be looking at the critical number practice for that. This is just a more complicated function. But to simplify this, you could factor out an x minus 4. And then you'd have 2x to the 4/5 plus 4/5 x to the negative 1/5 times x minus 4 to the first. And then that would actually give you, I mean, this then is one factor, so you could set that equal to 0. That would give you one of your critical numbers. Simplifying this further, yeah, x equals 4 is one of them. I'm looking at simplifying this second term here. So if I distributed the 4/5 x to the negative 1/5, and this here is x to the first, so it'd be 5/5. So when I distribute it here and I add these together, that's 4/5 x to the 4/5. And then it would be minus, and when I multiply that by 4, yeah, and that would still be to the negative 1/5. So that would allow us to combine these. Yeah, we'll stop here. I'll pick up with this tomorrow, but I still want you to see how to simplify it. On the practice, the ending ones are the critical numbers. And again, as long as you know this, you should still be able to try those out. Even answers are already on Canvas.